Our question today comes from Christian Urban, and just for context, this question was asked in a comment on a video on another channel that gives a very brief description of the stack, and it uses this analogy of a stack of dinner plates. So here goes. Christian asks, I'm a little confused about how the stack operates. Could you please help me out? Let's say we create two variables of type U8 called x and y. 1, do they land on the stack so that y is at the top? And 2, if so, what happens when we try to access the value of x? From my understanding, it shouldn't be retrievable since it's at the bottom of the stack. Thanks in advance. Christian, thank you for your very clear and very polite question. And given this analogy of a stack of dinner plates, it totally makes sense that you'd find this a bit confusing. So first, let me give you a very brief answer to this question, but then I want to dig a bit deeper. To really understand borrowed references in Rust, it's helpful to have a clear picture of how the stack works. The simple answer to your question is the stack controls where in memory local variables are placed, but having more stuff placed on top doesn't prevent you from accessing the variables underneath. To use the dinner plate analogy, it's as though you can access any variable anytime just by getting at the edges of the plates. But honestly, I think this is one of those cases where instead of contorting an analogy to get at some understanding, it's easier just to describe the actual thing. The way the stack works is really pretty simple, and it's absolutely fundamental to how computers work, so let's get real. It's time for a segment I like to call
How Computers Work.
The first thing to understand is that the hardware doesn't really know about local variables or the stack or even functions. Those are all concepts created by the compiler. The hardware has memory and registers. Memory is just one big array of bytes. Each location in memory has an integer address. Memory can get complicated with virtual memory, page protection, L1 cache, L2 cache and all that shit, but fundamentally it's just a big array of bytes. Then there's registers. The registers are in the CPU core. Each register holds maybe 32 bits or 64 bits, and there's a fixed number of them. There's typically a few dozen. The size and number of registers is defined by the CPU architecture. The instruction set. Almost all instructions work directly with registers. So for example, an instruction might say, take register 3, add 12 to it, and put the result in register 2. There are arithmetic instructions and bitwise logical instructions, and there's also a special register that contains some flag bits that get set depending on the result of things like a compare instruction. Some instructions will also access memory, so a load instruction might take the value of register 5 as an address, subtract 8 from it, read the contents of memory at that address, and put the result in register 4. A store instruction might do the same thing to work out the address, but it writes a value from a register into memory at that address. These instructions are all being fetched from the part of memory that contains your program. There's a special purpose register called the program counter, or sometimes it's called the instruction pointer, and it holds the address in memory of the next instruction to fetch and execute. So it keeps track of where execution is up to, and usually it steps forward by one instruction at a time. But there are other instructions called branch instructions that cause the program counter to jump to a different address. And branch instructions can be conditional, meaning it may or may not take the branch depending on the state of the flag bits. So these are the raw materials from which computation is made. This stuff is all implemented directly in hardware. We have instructions that perform arithmetic and logical operations between registers. We have instructions that read and write memory. And we have branch instructions that control the flow of program execution. None of this enforces any particular idea of a stack or variables or even function calls. The hardware has no notion of any particular piece of memory being allocated or free or of holding data of any particular type. It's just an array of bytes. Everything needed to organize what's in memory is the responsibility of the program. So the compiler can generate code that accesses whatever memory it wants. There are no dinner plates.
There is no spoon.
Out of these basic operations, a programming language has to construct loops, if-then-else conditionals, functions, and returning from functions, local variables with types, static variables, dynamic allocation, dynamic dispatch, all the concepts we know and love. For any function you can write, the compiler has to generate the instructions to produce that behavior using a handful of registers and a big array of bytes that we call memory. So now, finally, we can talk about the stack. And we're talking here about the stack, not just any old stack data structure. So like in video number 7, we made a stack data structure with push and pop methods, but that's not what we're talking about here. The stack is more properly called the call stack or the execution stack, and it has several other names. The stack is baked deeply into every program, every function by the compiler. The purpose of the stack is to give us two things. First, it stores function return addresses, so we can have nested function calls, and when a function returns, we have the address of the code it needs to return to. And second, it provides storage space for local variables within functions. So when a function is called, it can have its own little piece of memory on the stack for that function call. Okay, let's talk about how the stack actually works. On pretty much every platform, there is a hardware register dedicated to the stack, and it's called the stack pointer. It's just the address in memory of the top of the stack. This makes the stack really fast. When a function gets called and it wants to allocate some space on the stack, it just adds an offset to the stack pointer. And it's a register, so it doesn't get any more lightweight than that. When the function returns, it just puts the stack pointer back to the value it had before. Registers are fast, and the compiler wants to make your program run as fast as possible. So wherever it can, the compiler will avoid using memory and just do things in registers. So if you write a function with local variables x and y that are just bytes, there's a very good chance these variables will be held in registers and they won't appear on the stack at all. When we say local variables are stored on the stack, what we really mean is if a local variable needs to be stored in memory, it will be on the stack. The compiler has quite a bit of leeway in how it optimizes your program. When variables do end up on the stack, the compiler can access any of them anytime just by adding an offset to the stack pointer. The chunk of memory a function allocates on the stack is called a stack frame. So if you have a function where main calls a function foo and foo calls an increment function, we'll have a stack frame for main, a stack frame for foo, and a stack frame for increment. And in each of those functions, if there are any local variables on the stack, they'll have a fixed location within the stack frame. In fact, let's build that program. So the increment function takes a mutable reference x that points to an integer. The foo function has a local variable n, and it calls increment with a mutable reference to n. We'd expect the stack to look like this. N is a local variable in foo, so it's at a fixed location within the foo stack frame. And increment gets a reference to n, so you can think of the stack frame for the increment function as having a local variable x that points to n. Take this picture with a grain of salt though, because there's a very good chance the compiler will optimize the hell out of this, at least when you compile in release mode. It'll probably inline the increment function and just use registers. But of course, if the object being mutated here is something bigger and more complicated than an integer, there's every chance it will be stored on the stack. I hope it's useful to have this picture in your mind when we're talking about borrowed references. Very often, a function will have a reference to a variable that's owned by a different function further down in the call stack, just like in this example. Rust's borrow checker makes sure that references are valid even when they pass through multiple boundaries between functions, and that works for returning references from functions as well as passing references into functions. The next video will be all about visualizing borrowed references. I think it'll be a fun one, so stay curious, and I'll see you soon.